Hello everyone, Guri, and this is a small brief lesson with regards to the arithmetic section of CAT, and we will focus on rational and irrational numbers and understand how you can learn them to form your intuition. Now, rational and irrational numbers are a very important part of the basic arithmetic and understanding of quantitative methods. So let's just look at examples and classification of what these numbers are. As you can see on the page, basically real numbers are numbers which can be located on a imaginary number line. Now any number that can be located on a number line would be classified as rational versus irrational. Essentially, rational numbers are numbers which could be represented as a fraction where p by q is the number representing the numerator and denominator. P and q are both integers, but the denominator q is a non-zero integer. Just backing up for a minute, integers are numbers 1, 2, 3, 4 up to infinity, which are represented on the number line towards the right of 0. Essentially, the idea of rational numbers is to gain an intuitive understanding of how fractions work. Some examples of rational numbers are 0.333, 0.434343, and other such numbers. So basically, if you decode them in decimal form, a good way to describe them would be a non-terminating decimal with a fixed pattern, and this fixed pattern is extremely crucial to understanding and gaining an intuitive understanding of the fraction. On the other hand, irrational numbers are basically decimal numbers which don't have a fixed pattern but go on forever. A brilliant example of that is root of 2, which evaluates to 1.4142 and so on and so forth, and you will never be able to discern a pattern to these. Another great example of a irrational number is pi, which is perhaps the most famous that has ever been introduced to man. Now, to develop an intuitive understanding, we need to understand how this rational number can actually be written in the form of p by q. Now, there might be a direct and straight question in CAT which will be helped solved by this. But even if there is not a straightforward question, this understanding will help you to solve a lot of other aptitude questions where you have to find the remainders, where you have to find the powers, the last digit of the powers, or you might use that in logical reasoning and deduction as well. So just let's look at a very basic example of how this might work. As you can see on the page, a great starting point is, let's convert 0.232323 to, which is a rational number by our definition of non-terminating fixed pattern decimal, into a p by q form. Now if you can look at the page, how you see is, let's say x is equal to 0.23, perhaps this method is also very basic, and this will also help other people who have not taken maths in class 11th and 12th to understand how very basic propositions of math are established. Now what we do here is basically multiplied by this number x by a number 100. The logic of choosing the number 100 to multiply is that there are two digits that are repeating constantly. So 232323, which is easily recognizable by the bar that I have put on these numbers. So because there are two digits which are repeating, we are multiplying the number by 100, which is basically 1 followed by two zeros. Now when you do this, what you get is 100x is equal to 23.2323, which is the repeating original pattern. Now what you have to do is simply subtract the second equation and the first equation. So if you take out x out of 100x, you get 99x on the left hand side, and if you deduct 22.232323, where 23 goes to infinity, from the original number 0.23, you are left with 23. It's now very basic removal of 99 to the right hand side, and we get easily x is equal to 23 by 99, and this is the perfect form in which this number can be represented as. Essentially what we have achieved here is to see how a fraction which is spelled in a decimal form can be retraced into a fraction. How this intuitively will help you is, when there is a comparison between two different numbers, if you can quickly convert them into a fraction and you can compare the decimal and the numerator, you can see which is a larger number, which is a smaller number, and even if there is not a direct question or answer linked to that, you can still use that in your logical reasoning and deduction. Now let's take a slightly more shortcut view and give you a trick how this might work and be helpful to you. If you can see on the top of the page, I have just written out a pattern where if a single digit is repeating, let's say 0.AAA, then you can have a shortcut that the p by q form will be a by 9. In the other case, if there are two digits repeating, the pattern would be AB by 99, and so on and so forth. Now the problem here occurs is if there is an unfixed number before the fixed pattern starts, and there I am trying to capture an example which is much simpler to understand and will give you a very quick shortcut here as well. Let's say we have to convert 0.2565656 to P by Q form. What we do here is, rather than getting two equations, we get three equations. So first we put down x is equal to 0.2565656. Then because there is one digit that is not repeating and is not part of the pattern, we multiply by 10, which is basically 1 followed by 1 0. What this does is distinguishes the non-repeating part and the repeating part before and after the decimal. This is very important to understand for the next step. Now we basically follow the principle of the last example, where now in 10x we have after the decimal the pattern repeating consistently. So now because two digits are repeating, we multiply this 10x by 100. 100 as again because 5 6 two digits are repeating. That gives us the third equation, 1000x is equal to 256.565656. Now in equation 2 and 3 we can see that after the decimal point the pattern is exactly the same. What we have to do next is very simple and intuitive. You basically subtract equation 2 out of equation 3. So 1000 minus 10x would give you 990x, and on the right side it would be, after the decimal portion would be subtracted completely, and what will be left will be 256 minus 2, which is 254. From there on in it's extremely simple. We move 990 to the next to the right hand side, and basically we get P by Q as 126 by 495. So here friends, it's very clear that what we have to isolate is the repeating digits, and we get them into a form where after the decimal point we can cancel them easily. Now just let's look at a very simple example and a shortcut of how, if there are non-repeating patterns, how can that be converted into P by Q form very quickly and in a short way. So here you can easily see that what you have to do is very simply, if there is a 0 before the decimal, you put down 0, plus you take the first non-repeating digit or the non-repeating number of digits and then repeating digits to 256. Out of that you subtract the non-repeating digits, which is 2, and in the decimal you put 9 2 times 9 because there are two digits repeating, 5 and 6, and 1 0 because there was one digit 2 that was repeating. So this is the answer that we will get again, 254 by 990. Just let's repeat it for another example. Let's say we are doing it for 0.47373. P by Q would simply be 0 because 0 is the number before the decimal. Then we will do 473 minus the non-repeating 4 and divided by again 99 and 0. 99 basically because we have two digits repeating, and 0 because we have one digit not repeating. This gives us a very clear-cut answer of 464 by 990. I hope this shortcut shows you that it is very simple to go from a decimal form to P by Q form. This number in P by Q form will be very helpful for you to visualize what the fraction is, and then to compare numbers and to compare various digits at the end or the remainders, etc. I hope this is helpful for you. I hope you like this video. I also hope that this takes you not just into the shortcut but also the thinking behind the shortcut, and hopefully in the next video we can go to understand how this can be implemented in various questions. Hope to see you soon.